مساء الخير الأول. مساء الخير. النهارده معانا very special speaker دكتور طارق. دكتور طارق يعني أخذ الدكتوراه سنة 2013 من جامعة هارفارد، وقبلها كان عمل أندر جراد في جامعة كورنيل. وبعد ما أخذ الدكتوراه راح بوست دكتور في MIT. MIT ده معهد في أمريكا، لو حد جاله ادميشن ما يروحش، لأن لو رجع مش هيديله الشهادة بتاعته لأنه معهد. اوكي. فبعد كده دكتور طارق راح برضه بوست دوك في بريتش كولومبيا، وبعد كده جامعه امستردام، وهو حاليا في كوين ميري. دكتور طارق يعني very highly accomplished Egyptian يعني في theoretical physics. وهو برضه معانا في السوبرفيجن بتاع طلبه رابعه. هو الثيسيس ادفايزر او سوبرفايزر بتاع توماس. ودكتور طارق برضو يعني is willing to help في الاسبكت ده بالنسبه للطلبه بتاعتنا. هو بعد التوك هيبقى غالبا متواجد في مكتب دكتور عمرو اللي هو S007 لو حد حابب يتكلم معاه وكده يعني. تمام. هو النهارده هيكلمنا على تايتل اللي هو is space time a material. دكتور طارق التوك بتاعته بالانجليزي، يمكن ان هو يميكس وكده. اللي عنده اي اسئله طبعا يتفضل وكده، وبعد التوك برضو لو في حد عنده اي اسئله يعني اهلا بقى.
كمل بالمايك ولا من غير مايك؟ مايك ماشي. هو النهارده هنتكلم في موضوع is space time a material، وانا من دلوقتي هكمل بالانجليزي عشان الفيزيكس ده برضو يعني انترناشونال، وفي OCW برضو هيتحط على الانترنت. بس يعني لو في اي اسئله جايه بالعربي يعني تمام، ممكن اترجمها للانترنت، وهنكمل بقى يعني هنكمل بميكس كده. ماشي؟ Is that okay? Okay, so today I'm going to talk about space-time and thinking about space-time like a material. And in order to do that, I need to make you understand what I mean by this question. What does the question even mean? So my goal today is to convince you that you should think of Einstein's equations as an experiment or as a material that you can perform experiments on. مين هنا شاف Einstein's equations قبل كده? Who here has seen Einstein's equations? Okay. It's okay. I'm not going to show Einstein's equations today. But I'm going to make you think that you can think of them like an experiment. Okay, so I need to explain first of all what I mean by experiments. مين هنا عمل experiment قبل كده? Who has done an experiment before in their lives? Okay, ماشي. That's good. Now we're getting somewhere. Okay, so I'm going to give you an example of one very famous experiment. And this is the discovery of how ferromagnets work. مين هنا عارف what is a ferromagnet? Okay, very good. Okay, so in 1895, not 1985, in 1895, it was understood that if you heat a magnet, if you put it under high temperatures, then a ferromagnet, something with a permanent magnetic moment, loses its magnetism above a certain temperature. That temperature is called the Curie temperature. Okay? So let's see how we can relate that to certain experiments. Okay, so the typical measurements we do in the lab are things like the specific heat. So the specific heat of an object is the response of the internal energy with respect to changes in the temperature. It's this first derivative of the energy with respect to the temperature. And you can relate it to the second derivative of the free energy with respect to the temperature. There's a very simple relationship that you can derive just using thermodynamics. And a second thing that we can measure for a ferromagnet is something called the magnetic susceptibility. The magnetic susceptibility is the difference, the change of the total magnetization of the magnetic object when you change the external magnetic field. So you put a ferromagnet in an external magnetic field, and then you vary the magnetic field, and you see how the total magnetization changes. And the total magnetization, the first derivative of the magnetization with respect to the magnetic field at zero magnetic field is what we call the susceptibility. Okay? And it was discovered, the way that we do the experiment is that when you vary the temperature that you are putting the magnet at, you find that both the magnetic susceptibility and the specific heat of the magnet blow up at some point. And this blow up point is the precise location of the Curie temperature, this place where the magnetization of a ferromagnet goes to zero. So this is how we define the Curie temperature. Okay? So we look at things like the magnetic susceptibility or the specific heat as a function of temperature, and we ask where does it go and blow up? Where does it get very, very large? And this is how we define the Curie temperature. We find it when the plot gets divergent. Okay? And these are some plots that I took from this paper. Okay, now we want to explain this phenomenon. We've observed that the susceptibility or the specific heat blows up at some temperature, and we need to understand how we can model this. Mafhum? Make sense? Okay. So how do we do that? Well, one way that we think about magnets is that they're a bunch of little small magnets in a lattice. And they're arranged maybe in a square. They don't have to be a square. They can be any shape, but here I drew it as a square. And first we think about something called the local magnetization as a function of the location within the magnet. Okay? So we model our big magnet with a permanent magnetic moment using a field called the magnetization. The magnetization depends on the location within the magnet. So for example, here, the magnetization is up. Here it's down, 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 up as a function of position. Okay? It's a very simple model, and we are going to treat all magnets have something called a local magnetization. We don't know what magnets look like microscopically. It's very difficult to look at them microscopically, but we have a belief that they behave something like this. And we're going to treat them like that. Very, very theoretical, cooked up random model. This is very, very far away from how it looks like in real life. Okay, now what do? We ask, what is the correlation between the local magnetization at some reference point, I'm going to call it 0, and some other place, I'm going to call it x. This is called a correlation function. Correlation function asks, if I measure magnetization x at point 0, what is it at this other point? And how are they related? And it's very simple. You don't need to have any idea about what is the underlying structure of the magnet to figure out that it has to look like this function in red. This function in red is the most general function that it can behave as a function of space. It just assumes that it decays as you go further and further away. That means that it's something called local. The further you get from point 0, the less correlated it should be because they're not close. So it has to go to 0. And then there are just some coefficients that you need to fix. This thing here we call psi, and this thing here we call eta. And the thing called psi is the correlation length. It's an intrinsic scale that measures, that is a property of the material. Tells you how far the correlations diverge. And of course, this quantity that we can cook up the correlation function is impossible to measure. I can't put a local, magnetic probe at point 0 and point x microscopically. It's very difficult. But nevertheless, we think about this object because it helps us connect to the experiment. How does that work? Well, if I just consider statistical mechanics, Has everybody taken statistical mechanics here? Yeah, everybody. Okay. Statistical mechanics, you compute a partition function, and the correlation function is simply the derivative of the partition function with respect to the local magnetization. And so you can derive that the magnetic susceptibility is just the integral of this correlation function. And so if you just compute the integral of this G over the entire magnet, then you'll see that it's proportional to the correlation length. And the proportionality is to the power of this other number, eta. So this is a way to relate the correlation length to the magnetic susceptibility. And we said before that the Curie temperature is where the susceptibility blows up. So if that's where if the susceptibility blows up at the Curie temperature, then the correlation length also has to blow up at the Curie temperature. So now we have a measure of the susceptibility in terms of what we call the correlation length. Now, all of this to say when we plot a function, we can fit it. So if we relate the susceptibility to a function of the temperature and it blows up, then we can say it blows up with some polynomial in the temperature. And the way that it blows up is some power nu. And so we can relate the model to the experimental result in this way. And so I'm sure if you studied statistical mechanics, you have seen the Ising model. Yes? Yes, that's how ferromagnets work. So the Ising model numbers are here. 0.6 and 0.05 for nu and eta. So that's what the Ising model in 3 dimensions predicts for these numbers, nu and eta, just by computing the correlation function using the Ising model. And this is what you find in the experiment. So this is why we think the Ising model is a good model for magnets. The real world is not made of little spins that point up and down, but it predicts very well the results from experiments. That's why we think of the Ising model as a good model. Make sense? Or have I lost everybody? Yes or no? Is everybody lost or is everybody with me? انتوا معايا ولا خلاص يعني؟
Which way does it from the two-state system, two-state spin up, spin down system? You said it's a good model and experimentally gives you results. How does it differ? You want to increase the complexity of the model, upgrading from a toy model of two-state system. And which way will you do this?
I mean, you can add many more bells and whistles. A real-world magnet is made of atoms. Atoms have many electrons in their orbitals. The orbitals have overlaps. You can do quantum chemistry. You can get very, very complicated with your model building. But nevertheless, you're probably not going to do better than this. Like, you have to consider that computational complexity versus simplicity is also something that you want for a model. And so you can add more degrees of freedom. It's just going to make your life more difficult. And there's this idea that simple models capture universal features. They're not really exact, but so long as they're good enough, then they're good. We like them. We can always complicate our models, but so long as we have a basic idea of what's going on and we can relate to experiment, then we think that that's good.
You said that the two-state, the spin up and the spin down is a realistic model for magnets. So what would be a more realistic?
Yeah, so the most realistic would be to treat them really like the atoms with all of the electrons filling the orbitals and the overlaps between the orbitals, SPDF orbitals and all that stuff. But that's very complicated to work with. And then you have to work with quantum wave functions of the electrons, how they overlap with the nearest atom in the lattice, the shape of the lattice, all very, very difficult stuff. But the point that I'm trying to get across with this is that you don't need to consider that. You do very well by just thinking of spins on a lattice, because you can see the predicted values from the Ising model versus the experimentally measured ones. And this is a super simple model. It just spins up and down on a lattice. Very, very simple. So it seems to do very well. And it seems to teach us a lot about how magnets work. This model is good enough for capturing the universal features of phase transitions. We can, of course, do better, but for the most crude of experiments, we don't have to. Any other questions? Okay, so I really wanted to get across this idea that simple, very simple models of spins with two states on a 3D lattice can predict real-world experiments. You know, when people tell you that a model is unrealistic, well, they don't, without further specifying what is meant by unrealistic, that's not a really meaningful statement. A model is realistic if you can use it to make predictions. If it doesn't make predictions that match with experiment, then maybe it's just not a good model for the experiment. It doesn't mean that it's unrealistic. And there are other good models, by the way, for this phase transition, the phase transition of how a magnet works. For example, there's a model called the Wilson-Fisher, which is a little bit more complicated. It does a little bit better than the Ising model, but for all intents and purposes, it's essentially the same model. Okay, so the point of today's talk is to convince you that we should think about the Einstein equations, which most of you have not seen. That's okay. You've heard about it, right? Everybody's heard about it. Everybody's heard about Einstein, I guess. Yeah? Okay. It's kind of famous. So the point of today is to persuade you that Einstein's equations are the experiment. And they're not the model. They're the experiment. Okay? And that what we have to do is to find the models. That's the point of today. Okay? So our job is to find the toy models that explain Einstein's equations. Okay, so there are very famous lectures by this guy, Sean Hartnell. He's now at Cambridge on holographic methods for condensed matter physics. Condensed matter physics is just physics of experiments like ferromagnets. And holographic methods is like using gravity to understand condensed matter physics. But today I'm going to go around and I'm going to tell you about condensed matter ways of thinking about holographic physics, which is gravity. Okay, so let's work on some examples. I'll give you some. Today we're going to go through examples one after the other. Hopefully each one adds a layer of complexity, but we're always going to keep it in the same spirit. Okay, so question, what do I mean by experimental data that we should look for in a gravitating system or in Einstein's equations? What is really meant? Okay, so the first place we'll look is gravity when in Euclidean signature. So Euclidean signature means, so Einstein is a theory of space and time, and we don't have to only work in space and time. You can just consider the curvature of space. And whenever you're only considering the curvature of space, that is a Euclidean system. Euclidean geometry is just the curvature of pure space. So here we're going to think about the curvature of a spatial manifold in 3 dimensions. And I'm going to add that the metric has to be constantly have constant negative curvature. So something that has negative curvature is like the inverse of a sphere. A sphere has positive curvature, and a negative curvature manifold is something like a hyperbolic plane. Okay? So we're going to consider no time, just Einstein's equations on a Euclidean in a Euclidean system with negative curvature. Okay? And Einstein's equations is a nonlinear partial differential equation for space, a geometric object with constant negative curvature in this situation. Okay? And we're just going to try to solve this equation. Okay, there are 2 solutions. So this thing that I wrote down right here is something called the metric. The metric tells you how to measure distances on the geometry. And there are two solutions of constant negative curvature in 3 dimensions. They look like like a donut, but a 3-dimensional donut. And the donut is the boundary. So the torus is the very far away in this 3-dimensional world, and then there is you can think of the inside of the donut as the rest of space. Okay, but it's all negatively curved. So what I'm drawing is not really how it looks. I'm just drawing how it looks at the edge of the space. Okay, and the edge of the space can be described by a donut. So the donut has 2 periodic directions, one that I've called beta over here, and one which I've called that has length L, the red and the blue. And the difference between them is that I can shrink the red circle to 0, but I can't shrink the blue circle to 0. Okay? It's the only thing that you need to know about this geometry. And there's another solution where those guys are swapped. I can shrink the beta guy to 0, and the blue guy can no longer be shrunk. And the two spaces have different notions of distance. So here, this tells you how to measure distances in one space-time. You see one equation. Here is a different one. The distances are clearly different because the equations are different. Okay. So, if I compute the action, you guys know what an action is? So, if I compute the action of these two geometries, then I find that at some point one becomes dominant over the other, and the partition function, which is the same partition function that you study in statistical mechanics, takes the following form. It's a very simple function. It has these two behaviors, whether beta is greater than L or less than L, up to factors of 2 pi. And this is a very simple function that I get out of Einstein's equations. It comes from these two geometries. What is being said is that as I vary L and beta, one geometry becomes more important than the other in the statistical ensemble. Okay, and this is the function of the free energy, or the log of the partition function. It behaves like this. And if I look at my partition function, it satisfies a very simple relationship. It's equal to itself if I take beta to L squared over beta. You can just stare at this equation, and you'll see that this is true of this function.
What are we sampling?
You're sampling over geometries. That's right. So then you have to just ask which one is the dominant one, has the bigger free energy, and in that case, you just keep that one, and then as you vary the parameters, you keep the other one.
And the action I'm calculating is the action that is supposedly give me.
Yeah, it's the one that you get the equations from. So it's the Einstein-Hilbert action.
Obviously, like addition, the partition function is based on just linked to Hilbert energy.
Yeah, so this is something I didn't tell you, but these in Euclidean signature, this beta is you should think of as the temperature, the inverse temperature. So when you get rid of time and you make it a compact coordinate, it just so happens, this is something that you'll learn in quantum field theory, that the periodicity of what one of the directions can be thought of as a thermal direction. It's just
Just related to the motion.
I can't hear you.
Is it related to the motion and object in space time, or just something?
No, it's different. It's so this would be the temperature if we were to look at, for example, real-time dynamics in this ensemble. There's another way to say it is these geometries are related to black holes, and black holes themselves have a temperature, and this would be the temperature felt by objects outside of the black hole. But we don't have to go there. The only important thing that I wanted to say was that this statistical ensemble obeys this relationship, that the inverse so beta is the inverse temperature, and you can take beta to 1 over beta with some factors of L here, and the partition function stays the same. So this tells you that the low temperature physics and the high temperature physics are related. So if this is a statistical ensemble, this is a statistical ensemble where the low temperature phase and the high temperature phase are the same. So this is something that is a result of a calculation that you use in gravity, and now we want to find a system that can explain this kind of physics. Now, of course, I didn't explain to you why this is a temperature, so maybe I'll take a second to do that. So let's see, what's the best way to explain that this is related to an inverse temperature? Yeah, okay. Have you guys taken quantum mechanics? Okay. So have you guys seen the path integral formulation of quantum mechanics? Okay. So
he started by studying the case where he could change the concept here,
yes.
and then they found there's two solutions, and this is the partition from the UCW. Where did I get the idea to send him over there?
Yeah, so here we're treating Einstein's equations like our like in the Ising model, you have a Hamiltonian. So here we're treating the Einstein-Hilbert action as the Hamiltonian in the statistical ensemble. And then summing over the geometries is like doing the statistical sum in statistical physics. So we're treating Einstein's theory like a statistical ensemble at a finite temperature. And then this periodicity of the geometry is related to the temperature. Yeah, you have to imagine that there is some experimenter, and they have a physical system whose dynamics is explained by Einstein's equations, and they want to understand what happens as you heat up that system. It's a complete, it's just a thought experiment. You can't build this in the real world. Any other questions? So I was going to say that if you study statistical physics and quantum mechanics, they're actually related if you analytically continue this inverse temperature into time. So transition functions in quantum mechanics, tunneling amplitudes and all of that, you can think of as being related to thermal physics in statistical physics by some process called analytic continuation, where you take this beta and to imaginary values, and then it describes real-time physics. I'm certain that that wasn't a very satisfactory explanation, but it's the best I could do in this short. Anyway, so what we want to do is now we have this experimental result that the low temperature physics and the high temperature physics are related, and we want to find a toy model that matches that experimental result. So it turns out that there are some quantum systems that are invariant under something called an angle-preserving transformation. So this is an example, a picture of an angle-preserving transformation. So if I apply some map F from this grid over here, of course I've warped the entire shape, but I have preserved that there's a right angle between all of the lines. So that's a angle-preserving transformation. And the angle-preserving maps in 2 dimensions is an infinite set of maps. There are infinite numbers of these types of maps. You can find an infinite number of maps that preserve the angles between lines in 2 dimensions. So if I have a 2-dimensional system that is invariant, that has as a symmetry that if I do one of these angle-preserving maps, the system doesn't change, then it turns out that my partition function has to satisfy this relationship. That if I define my partition function, which is the sum over all states weighted by the energy with inverse temperature beta. And if I just write beta, and this is the angular momentum, you can also add angular momentum to the system. It turns out that if my system is invariant under these angle-preserving transformations, then my partition function, written in terms of these variables right here, tau and tau bar, you see there's an I, so tau bar is just the complex conjugate. Then because of the infinite amount of symmetry, then for any A, B, C, and D that satisfy this relationship, my partition function will transform like this. You'll find that for any A, B, C, and D, you'll get the same function once you transform tau and tau bar like this. And so that tells you that, for example, if I set A, B, and D to 0 and C to -1, then I have a system that takes tau to 1 over tau. It's like beta goes to 1 over beta. So this is a very famous correspondence that was discovered 25 years ago called the anti-de Sitter conformal field theory correspondence. So conformal field theories are quantum theories that are invariant under these angle-preserving maps. And anti-de Sitter are these geometries that have constant negative curvature. And so there is a known duality that takes a quantum field theory that's invariant under angle-preserving maps in, for example, 2 dimensions, and relates it to a constantly negative curved geometry in 3 dimensions. And so here's an example where you could have discovered that this relationship is true just by noticing that treating gravity as an ensemble leads you to this kind of relationship between the partition functions. It's kind of a magical thing. Are there any questions about that? So the idea is that if you have a partition function that obeys something like this, the low temperature phase and the high temperature phase, then what happens is that it has to be related to a system that's invariant under these angle-preserving maps. So you would be able to describe it in terms of a system that doesn't have gravity at all, just has to be one of these systems that has this kind of symmetry. Okay. Are there any questions about that example? Okay, so let's go to a second example. This one is slightly different. This one is about black holes as they collapse. Okay, so one thing that so have you guys heard of the Hawking information paradox? You tell me what it is. Can anybody tell me what it is? In the front, maybe? Any idea?
It's about the code objects. لما حاجات بتخش ده كله ما ينفعش تطلع فده معناه ان في انفورميشنز بتفرق
صح صح
فهو ممكن قال ان ده غلط ما ينفعش يحصل
بالضبط هي الفكرة. The idea of the black hole information paradox is that if you have for example, if you have information that you are keeping, you can destroy it by throwing it into a black hole. But we know that in all of our physical experiments that we have done so far, the physical experiments are the equations that describe the physical experiments all are reversible. So you can always reverse time and the laws of physics stay the same. And black holes are the one place in nature where we seem to not have this capability. There's absolutely no way of recovering information from a black hole, which seems to violate what we think should be a law of physics, that all processes should be reversible. All fundamental processes. So Black holes, when we think about them from Einstein's equations perspective, they lead to deep paradoxes in the way that we understand the fundamental laws of physics. Because black holes seem to destroy information. So we need to figure out how to think about black holes. So of course, we don't know how to do that. This is a many-year program trying to understand the black hole information paradox. So what we're going to do is we're going to try to learn as much as we can about black holes without first solving the problem, but just come up with a simple model to describe some very basic things about black holes.
I would say something like this graph if I'm saying if you get forcing solution for the black hole and get the energy geodesics or so when you launch and getting otherwise the ground you get the logarithmic RT relation, meaning if you throw a part correction inside the black hole it will get a resultant behavior around the forcing singularity. So that means for it to throw inside the black hole will never go beyond the positively isolated region and the positively selected region. So where exactly does the paradox go?
Are you asking with respect to the exterior time you never see the particle enter the black hole?
Yes, never. That's never.
Yeah, so that's a problem with the coordinates. So there are coordinates that go through. So for example, if you use the extended Kruskal coordinates, then those are better adapted to describing processes that go into the black hole. It's true that as a particle or an object that you throw at the black hole gets closer and closer to the black hole, it looks like it gets pancaked onto it, but it actually goes in, and you do lose the information. At some point, there's a redshift. The redshift becomes very dark, and you won't be able to use any detector to notice this object, and the thing becomes black. So it all depends on the sensitivity of your equipment, but at some point you lose access to the object.
The point of angle resolution that's just for 2D, or we can go for 3D.
So in 3D also there is this relationship. There's the relationship between negatively curved geometries and systems that are that are invariant under angle preserving maps.
For example, in high dimensions, so we can make a projection, lower dimensions, and
No, it works. It works there too. Yeah, I was only giving an example of 3D and 2D because I can draw 2D angle preserving maps, but the relationship holds in higher dimensions. It's just that in 2 dimensions, the number of angle preserving maps is infinite, and so it's more powerful. But in higher dimensions, there's a finite number of them.
so we can make projection from higher dimensions to lower dimensions. Synthesis.
Yes, but these projections lose information. So you usually want to keep as many dimensions as are relevant to your physical system. Okay, so we don't know how to solve the information paradox. Very difficult problem to solve. So what we're going to try to do is we're just going to try to understand simple toy models for black holes, just like the spin up, spin down type understanding of ferromagnetism, which, as we all agreed, is a very crude approximation. Okay, so we're going to try to make crude approximations about black holes. So what we're going to try to do is we're going to try to use Einstein's equations to extract very crude, simple experimental curves, just like the divergence of the magnetization, and then try to match it using a different toy model. Okay, so here's an example. This is from a paper of mine from 2016 and 2017. So the solid curves in blue and yellow, these are curves that you can derive from Einstein's equations about like what is the correlation between an object that is thrown from very far away to the black hole and how it relates to as it enters the black hole. And as you can see, the correlation decays, which tells you, besides this this point, which is this light cone singularity, but But the correlations decay, that tells you that the black hole is absorbing the particle. The decay of the correlation function is how you can tell that the black hole is absorbing the particle. And the solid curve is what you get from Einstein's equations. And the dotted curve is a toy model of that you can derive by considering a system invariant under angle preserving maps. So here you can see a very simple example where a completely different system, just invariant under these angle preserving transformations, gives you the exact same curve that shows also this like absorption of the black hole. And this mechanism explains a lot about how we understand this fact about absorption. It doesn't tell us how the information gets out, because in principle, in the angle preserving system, it will, but it requires very, very, very fine-tuned information that's very hard to calculate in practice, but is not impossible to calculate in principle. So here's an example where we have a good toy model for a black hole that falls in that has nothing to do with Einstein's equation. I want to mention that the solid curves are from Einstein's equations. The red dots are not. Completely different system. It's like the up and down arrows, just a little bit more complicated. Up and down arrows invariant under angle preserving maps, but it behaves exactly like a black hole. So here's an example where you use Einstein's equations to derive a curve, and then we try to find a toy model that matches the curve. And here's a very nice example where we can do that. Is that clear? So we're going to keep trying to do that. So we're gonna continue along this vein. We're gonna do another example that involves black holes, and probably some of you know this, but it's good to give you a little bit of a flavor of how black holes behave. Black holes are objects that have a temperature. So this is something that was discovered by Hawking himself. It's part of the Hawking information paradox also, because if you throw so black holes are not absolutely black. Classically, they're black, but if you add quantum mechanics, they start to radiate and shrink, but the radiation is thermal. So the radiation is the same no matter what you threw into the black hole. And that's part of the problem. So if we understood the equations properly, the black hole would radiate in a way that was dependent on what was used to form the black hole and how it was created. But our current understanding of how radiation works is that all of the initial conditions are washed away, and the radiation of the black hole is just black body thermal radiation. So black holes are objects that we know have a temperature. The temperature comes from a quantum mechanical effect, and the temperature is controlled by a combination of the mass of the black hole, its charge, and its spin. So black holes can be spun, they can have spin, they rotate, they can also have charge, electric charge, and of course they have mass. So the temperature of the black hole depends on all of these parameters. Okay, and now I need to tell you another thing about black holes, is that black holes are objects where there's an event horizon. And if there's a black hole next to you, there's an idea that there's a distance between you and the black hole. That distance is measured by something called the proper distance, or the proper time that it would take you in your reference frame to fall into the black hole. So the distance or the time that it would take for you to fall into the black hole is called the proper distance or the proper time. And if I take the temperature of the black hole to 0, I can cool the black hole to 0 temperature. That proper distance goes to infinity. So it takes an infinite amount of time for somebody to fall into a 0 temperature black hole. This is something very, very strange. So black holes can be made 0 temperature, and once they're at 0 temperature, you try to fall in and you'll fall for an infinite amount of time. You'll die before you fall in. Kind of crazy. But the interesting thing about these very cold black holes is that they have very interesting thermodynamics. So the interesting thermodynamics of very cold black holes is found in this relationship. So do you guys remember that I called this thing CT the specific heat? So the specific heat is how the internal energy of a object changes as you raise the temperature slightly. And cold black holes have specific heat that is linear in the temperature. Linear in the temperature is very strange. There's almost no systems in nature that have linear in temperature specific heat. So it's very hard to model. The only known models that we have for these linear in temperatures systems are free fermions. So that's like if the electrons in a metal were completely free and not interacting. And the other system are systems that are invariant under angle preserving maps. So this is something that maybe you guys are witnessing that is a recurring theme in this talk, is that these angle preserving maps, which is also called the conformal symmetry, controls a lot of things. So not only does it control three-dimensional systems that have low temperature and high temperature relation, but also low temperature systems that have linear specific heat. So we would like to come up with an understanding of the thermodynamics of these very cold black holes that take an infinite amount of time to fall into. Okay, so it turns out that when I cool these black holes, the black holes themselves generate a geometry that has these angle preserving transformations. So if I try to fall into a very cold black hole, I get teleported into a universe that is very strange because all angles get very strained. Like there's no sizes that make any sense. It's part of why it takes an infinite amount of time to fall into this black hole. The geometry gets super warped, very strange world that you would fall into. And it's kind of magical because actually these systems exist in the real world. So very highly spinning black holes are systems like this, where it would take you an infinite amount of time to fall in, and your entire body would get warped in a very strange way. And there's a very simple symmetry that comes along with these black holes, and it's something called the special linear transformations. This is a smaller version of all the angle preserving maps in 2D. It's the angle preserving maps of the line. And systems with this kind of symmetry could explain the linear and temperature specific heat for a cold black hole, if we can come up with a model. So in a paper from 2013, when I was a PhD student, we had a hypothesis that, for example, if we had a completely random Hamiltonian, you could generate such a symmetry, this SL2R symmetry, to describe these kind of black holes. And then a few years later, somebody wrote down a model, these three guys, actually very famous professors, they wrote down a model that describes the black holes. So here I'm writing the Lagrangian for you. You guys have seen Lagrangians before? So these are Lagrangian. This Lagrangian is described by just n fermions. It's just a quantum mechanics of n fermions coupled with this potential over here. So this describes the potential that couples the n fermions, and the coupling constants are completely random. We can choose them to be totally random. And on average, this system behaves exactly like a cold black hole. It develops, on average, this symmetry that I called SL2R. So you can see here I'm writing down a model. It looks nothing like a black hole. It's just a bunch of fermions that interact with a random interaction. And this model, magically, is very successful at describing the thermodynamics of cold black holes. Well, this is actually the free energy. So the free energy is like the thermal partition function, the log of the thermal partition function. So this is like the Lagrangian, except for kinetic minus potential, it's kinetic plus potential. Because in the partition function, we have the energy, not the Lagrangian. But this still describes the thermodynamics of this system. This is just the energy of the system, not the Lagrangian. And this beta is again related to the temperature. So the system of fermions coupled with a random interaction is extremely successful. There are actually thousands of papers, maybe like tens of thousands of papers, that use this and match between this model of fermions and black holes, cold black holes, and it's kind of a incredible development. And all that you needed to know about cold black holes was that they develop this symmetry at very low temperatures. And the symmetry is what explains this linear and T-specific heat. So the first thing you have to do is look at a black hole and at very low temperatures, measure its specific heat. You find, and the specific heat you derive from Einstein's equations. You find that it's linear. Linear specific heat is very weird. We need to come up with a model. It was very hard to come up with a model of linear specific heat. People tried for many years. And this is one that they landed on. It's called the Sachdev-Yekitaev model. Extremely successful at describing the low temperature phase of black holes. And as you can see, has nothing to do with black holes. Nothing. It's just a bunch of fermions. Okay. So let's try to spice up that model a little bit. So,
what do you mean about statistically formula?
what do I mean?
What's needed?
So, for example, what I mean is if you try to understand how it deforms or how it reacts to throwing stuff in, you can do a bunch of calculations of these things I called correlation functions. The correlation functions measure how the black hole reacts to perturbations, so on and so forth. And this simple toy model can capture a lot of those correlation functions, how the black hole reacts to these kind of perturbations. And it's very non-trivial. I mean, we want to have very simple toy models that can explain these black holes that don't rely on Einstein's equations, because we know that there are problems with Einstein's equations, particularly when you try to go in the quantum regime. So we're trying to come up with models that behave on the whole like systems that you find in Einstein's equations, but at the same time, we know how to quantize this. So this is why this is an attractive model, because not only does it explain things that we understand, that we can match, but it lets us go beyond the match. Are there any other questions? Okay. So now we're going to try to spice up this model. So remember, I mentioned that black holes have a mass, they have a charge, they can have a spin, and in 3+1 dimensions in the universe that we live in, if I fix this relationship between the mass, the charge, and the angular momentum J, then my black hole will be stuck at 0 temperature. So I can vary the charge and the angular momentum so long as I fix the mass in this relationship, and I can stay at 0 temperature. And remember, 0 temperature is exactly where a model like this is accurate. So we want to see if we can understand how to understand the spinning black hole at 0 temperature as we vary its charge and angular momentum. So let me show you a curve that you can derive from Einstein's equations. So this is a curve of the angular momentum versus the angular velocity of a 0 temperature black hole. So that means that it's along this curve where m squared is related to the charge and angular momentum via this equation. And you see as you increase the angular velocity at 0 temperature, then the angular momentum goes up. That makes sense. All of you guys should see that, because angular momentum is r cross p. So as p increases, angular momentum increases, right? You guys remember that equation? Okay. And then it starts to go down at some point. The angular momentum curve has a max, and then it comes down. Well, so what is this curve over here? This curve also is logically makes sense. Angular momentum is r cross p. So I can have a very slowly rotating black hole. So long as it's very, very big, then it can have a very large angular momentum. The angular velocity can be very small, but if the black hole is very large, then its angular momentum can be still very large, even though it's very slowly rotating. So that's this part of the curve. So very small black holes, to increase their angular momentum, you just have to spin them up. But at some point, you can't spin them up indefinitely and stay at zero temperature. And this is the point that is very interesting, that at zero temperature, there is a max velocity for black holes. If I try to spin a zero temperature black hole and stay at zero temperature, so you can imagine I have a black hole, I put it in a bucket of ice, and I try to spin it just like in that picture. At some point, I can't spin it faster than some maximum value. And that's very strange. How do we describe a system like that? What are there systems that behave like this? It's very interesting to try to come up with a model that does this. So let me tell you how we try to further investigate this. So if I take a derivative of the angular momentum with respect to the angular velocity, then it obeys this relationship. So you can see that if I increase the angular momentum too much, the first derivative of the angular velocity diverges when omega squared goes to 1 over 8 q squared. So this denominator goes to 0, and there is a critical exponent, which is minus 1/2 for this first derivative. So this is an experimental result that we want to explain using a toy model. So we're going to try to use this type of free fermion model with a random interaction and see how far we can get. So here I'll show you an example of a model that we studied, which is very similar to the previous model, but it allows us to have spin. So you need to add a parameter for spin, and that's just that it has a rotational invariance. And you can break the rotational invariance to get spin. So this SO3 is the rotation symmetry in 3 dimensions. And so we just changed the model so that it has a rotation symmetry. And then we broke the rotational invariance. And what we found was we couldn't match the behavior from the black holes anymore. So we could match the critical exponent, but in our model, the critical exponent was minus 1/2, but it was not the first derivative that diverged, but the second derivative. So that's to say, if any of you want to try, then you should, because this is an open problem that nobody has solved. Very simple. How do you describe the behavior of a very cold black hole as you try to spin it up? Can anybody find a toy model? And I invite all of you to try, because it would be great if somebody could answer this question. Are there any questions about that? Okay. I think I'm over time, by the way. عادي؟ أكمل؟ Okay. فاضل مثلا 2 examples. There's only 2 or so examples left. Okay. So the next example is something that also happens in when you have cold black holes. So in 1947, these 2 people, Majumdar and Papapetru, they discovered a new class of exact solutions to Einstein's equations in 4 dimensions. And the equations are for cold black holes that have, so remember, a black hole can be set to 0 temperature if it's not spinning, if its charge is equal to its mass. Okay? So if the charge of the black hole is equal to its mass, then the black hole is at 0 temperature. And what's interesting about that is that if I have two black holes whose charge is equal to its mass, then I can position them however I want. They don't affect each other because the gravitational attraction cancels the electromagnetic repulsion. So these guys in 1947 realized that that means that I can put any number of mass equal to their charged black holes around, and that's an exact solution to Einstein's equation. So the H is you just assume that Einstein's equations look like this, or the metric of the space-time looks like this. You plug it into Einstein's equation. You make sure that your vector potential for your electromagnetic field has the same function H. And then if you plug this into Einstein's equations, coupled to electromagnetism, then you find that this H has to satisfy a very simple equation, that its Laplacian is equal to 0. So the general solution to that is just this function, where the Q is the charge of each black hole, or its mass. It's the same thing.
What's the motivation for this answer?
It was a guess. The guess was, okay, space-time is isotropic, so it's just one function in front of all the directions. And then they tried many different things, and they landed on this guess. I don't have a better answer for you because, with many of these solutions to Einstein's equations, the idea is to just guess and check. It's a nonlinear equation, very difficult to solve. You sometimes get lucky if you try the right ansatz. So this was a case where they tried the right ansatz, and they found that Einstein's equations boiled down to just this simple equation. Lucky? We know how to solve this. So this is a system where you can solve Einstein's equations exactly, and you find that there are many solutions that are parametrized by the masses or the charges of the black holes and their positions. Okay. And the reason that we have this this 1 in front is because we wanted very large distances to have flat space. So at very large distances, this becomes just the Minkowski metric, which is the metric of flat space. And so that's why you want the 1. But the 1 is not necessary to solve the equations. You can also delete the 1, and you're still solving the equations correctly. So we're going to now delete the 1. And instead of having flat space, we have a different space, which is this anti-de Sitter 2 times the sphere. So you don't have to understand what those words mean, but you should just know that if we delete the 1, that very far away, you look like you're still close, very close to a 0 temperature black hole. Remember, I told you that a 0 temperature black hole, there's an infinite amount of time that you would spend falling in if you tried to fall in. Well, if you begin to fall in, that's this ADS2 times S2 geometry. So if I delete the 1, then I'm still within the basin of attraction of one very cold black hole. So I'm going to show you a picture of that. So here are two solutions to the same equations. One is where this H is Q1 plus Q2 divided by R. And that's just like if you're falling into one very cold black hole of mass Q1 plus Q2. Or we can have two black holes, one of charge Q1 and one of charge Q2. And the geometry would look like this. Very far away, it would look like this geometry over here. But as you fall closer and closer to the black holes, eventually you would have to choose which black hole you fall into, either this one or this one. And the difference between these two geometries is that this one is, we call it a single black hole, and this we call a fragmented black hole. So that is to say that these two geometries very far away are the same, but as you fall in, they then begin to appear different. Okay? And if we're trying to understand Einstein's equations, then we should be able to have a model that describes both of these phases. So what could be the physics of this kind of phase? Actually, there's one more thing I want to tell you, is that these geometries are not separate. These geometries, you might think of them as separate classically. They're different geometries classically, but quantum mechanically, they're not separate. You guys have heard of quantum tunneling? Yeah, you study that in quantum mechanics. So geometries can also tunnel when you have quantum mechanics and general relativity, and there exists a tunneling amplitude to go from the single black hole to two black holes, and that's called a tunneling transition. So the black holes themselves are not at zero temperature are not necessarily stable quantum mechanically. They want to fragment, and it's a known fact about this system of black holes at zero temperature at fixed charge is that single black holes want to fragment. They want to break up, and it's very hard to model that. What kind of physics of the toy model do we need to incorporate in order to describe a system that wants to fragment and become very weird looking, like amorphous type of object? So here's the type of picture. If I have a black hole, it has mass equal to its charge. As I lower the temperature, what will start to happen is that the black hole will want to form a black hole galaxy. Will want to fragment into a bunch of different black holes. And so this is the thing that these black holes by Majumdar and Papapetro make us need to study. We have to understand. If we understand these types of systems, then we will understand this transition. So we have to come up with systems that model this transition. But it's very difficult to come up with an order parameter for this transition, because, as I mentioned, it takes an infinite amount of time to fall into these black holes. So if you're trying to do your experiments from out here, it's very, very hard to measure any difference between these two geometries. So it's very hard to find an order parameter like the Curie temperature or the magnetic susceptibility that distinguishes between these two geometries. So that is to say that understanding this transition is a very difficult problem, and it's still unsolved. Okay, so I encourage all of you to think about this problem and try to come up with a model for it, because I tried for years and failed. Okay, so but I can give you some ideas. So one idea is that a model that wants to fragment like this is a model that behaves like a glass. Do you guys know what a glass is? You guys have seen glass before? You guys know what makes the glass different from a metal or a different other solid? I hear some ideas. Anybody? Say its structure. Yeah. So glass does not have periodic structure. It's an amorphous solid. And it's actually also an unsolved problem to understand the transition from liquid to glass. It's a famously very difficult problem. It should be a millennium problem, but it's unfortunately not. But what we do know about glasses is that they have very, very complicated free energy landscapes. So the free energy of the glass. So for example, in the Ising model, at low temperatures, the free energy just has two states, all up and all down. Very simple free energy landscape. But a glass is a model that has a free energy that is very complicated, many states that are approximately the same energy. And so that is to say, perhaps these fragmented solutions have something to do with the amorphous, fragmented nature of glass. So perhaps the types of models that we need to describe very cold black holes at fixed charge are potentially a glass. And I tried for many years. Here are some of my papers where we tried to explore this idea, but it's very difficult. Still open question. You guys should definitely try to solve it. Here is an attempt that you guys should maybe link to the previous version, but it turns out that if you, instead of considering a free energy made out of fermions, you consider a free energy made out of bosons with a random potential, then this model is known to behave like a glass at low temperatures. So one idea was to try to use this to model the black holes at very low temperatures, but still, it doesn't quite work. Okay, there's so many interesting plots that you can draw, but they simply just very difficult to match them to anything in the black hole geometry. Okay, last example. So the next example involves de Sitter space. Have you guys heard of de Sitter space? No? Nobody knows about de Sitter space? De Sitter space is one of the earliest geometries that was ever written down that solves Einstein's equations. It solves Einstein's equations with a positive cosmological constant, and it turns out that it's the geometry of our universe. Our universe is expanding, and the expansion rate is exponential. And this is a drawing by the guy who discovered the geometry, who wrote down the solution himself. His name is Wilhelm de Sitter, and he asked, who's blowing the balloon? And it just describes a universe that is accelerating, whose volume is expanding at an exponential rate. And when you live in a universe whose volume is expanding at an exponential rate, then what happens is that the further something is from you, eventually you stop seeing it. It just moves away from you too quickly. You stop seeing it. So there is like an event horizon. It's very similar to a black hole, but it's caused by the expansion of space-time.
Most indications of the expansion of space-time, it's usually known as a balloon, but what would the shape of the universe actually look like? It's not be very subject to say it's sphere.
Well, you mean the spatial volume?
Yeah.
I mean, the problem is that we can't see what it is. We can't see because beyond a certain point, things are moving too far away. We can't tell if we live on a sphere or if we live on the plane.
And where do we get the idea that the expansion is isotropic across all directions?
Well, we look and we see that it is. That's what we do. We measure all directions in the sky and we see that it's the same. Any other questions? Okay. So it was discovered in 1998 and then awarded the Nobel Prize in 2011 that actually our universe is like this. Our universe is expanding at this exponential rate. These are the people who got the prize. They don't deserve it because, of course, science is collaborative and there were thousands of people working on this experiment, but 3 white guys get the prize. It's always the case. So that's how it is. These are geometries. They solve Einstein's equations. Let's try to understand them as best we can, and let's try to come up with toy models. So this type of expanding spacetime is called de Sitter. And if I try to put a black hole in de Sitter, well, they have a maximum size. They can't get bigger than a certain size because and the maximum size is set by the fact that there is only a certain amount that I can see beyond which things fall out of causal contact. And the maximum size of the black hole is basically making sure that the left side of the black hole and the right side of the black hole are not out of causal contact. So that's the maximum size of the black hole. So now let's try to do the same measurement that we did before. We try to spin up the black hole, keep it at 0 temperature, and make sure that it's the maximum size. These maximum size black holes also have 0 temperature. And now I have the exact same plot as before, the angular momentum as a function of the angular velocity, just on its side. So I increase the angular velocity, the angular momentum increases, and then at some point the angular momentum starts to decrease. I have no idea how that can be possible. I don't understand a physical phenomenon that explains how, a black hole of finite size, I increase the angular velocity as much as I want, and the more angular velocity I add, the less angular momentum I have. This is a plot that you can derive from Einstein's equations. I have no idea what you would need to add to a toy model to explain this. So here's a homework problem for you. Go home and find a model that can explain this plot. Okay. The last, I forgot that there was a seventh example. This is this one is quick. Also, there is a fragmentation instability, just like in flat space, for black holes in de Sitter. And again, what is the phase that explains them? We have no idea even what the simplest toy model for a black hole in de Sitter is. What might be this fragmentation instability for a black hole, for several black holes in de Sitter? No clue. Okay. So there are many interesting things that we could discuss about de Sitter, but I think it's time to conclude. So let me give you my concluding remarks. So number one, you should treat Einstein's equations like a laboratory, and that's it.
Not just ideas, but I didn't see in all of this where the idea of the space-time itself.
Yeah, so the space-time is all these plots that I derived, like this one, you get it from a space-time. You get it from a geometry, a black hole solution. So that's the material that I'm experimenting on. It's like think about the ferromagnet. Think about the ferromagnet. So the ferromagnet is an object that I measure, and I get a curve out of it. So the thing that gives me the curve, the experimental curve, that's the material. So Einstein's equations is the thing that gives me the experimental curve. So that's the material.
How can you detect the temperature black hole and what makes significant analysis design?
What was the second part?
How can we detect the presence of certain pitch black hole and what its significance in this?
So a zero temperature black hole, for example, would be one where so for example, if we measure its mass and we measure its angular momentum, then there would be a relationship between the mass and the angular momentum. So for example, there is for a fixed mass, there is a maximum angular momentum for a black hole. And at that maximum angular momentum, the black hole is at zero temperature. So if we measure the angular momentum of a black hole and its mass, then we can determine whether or not it's zero temperature or not.
It cannot take the presence of the black hole without radiation.
No, we can. We have measured many black holes, and we keep measuring them nowadays. For example, LIGO measures black hole mergers, so you can fit the parameters of the black hole, for example, its mass and angular momentum, to the ring down that they measure at LIGO. That's one way of measuring these parameters.
The specific definition of temperature is beta volunteers portion asymptotically. So applying a zero temperature black hole says something about the probably very low number of microscopes. What can I use covenant space phenomenon?
Keep going. Finish your question.
No, I know the second question.
So was the question, how do we explain the fact that there is an entropy for a black hole at zero temperature?
Yes. How do you reconcile that's the asking of black hole with the fact that it's
Derivative with respect to the energy is zero. So I don't think that the derivative of the, yeah, I think there are two different things. So let me just try to be, yeah. So black holes have an entropy. So there's a first law of thermodynamics related to black holes. This was first guessed by Wheeler and Bekenstein, and then derived. Okay. So so the idea is that the change in the energy is related to T times the change in the entropy. The changes can be zero without the entropies being zero themselves. There can be a constant shift. And it's understood for black holes that the microcanonical entropy of a black hole is proportional to its area. And at zero temperature, the area is not zero. So the entropy of a black hole is non-zero at zero temperature, which is, again, one of these things that we have a lot of trouble explaining. Very few systems have high entropy at zero temperature. Among the systems that do well at explaining that are these systems with angle preserving, that are invariant under angle preserving transformations. And the reason that is because low temperature and high temperature are related. So you can have high temperature, high entropy at high temperature. And if you can relate high temperature to low temperature, then you also have to have high entropy at low temperature. It's one of the ways that people understand this. There was a second question?
I just want to measure the magic results for the spinning black hole.
For the spinning black hole.
There's the one where we said that in H is the only parameter in the matrix that's always not spinning.
Yeah, that one is not spinning. So this is just mass and charge. There is angular momentum in the geometry. No, there's no angular momentum in this geometry.
The metric comments about the entropy, so that's like measure room not down. But is that the sign of the background when they talk about entropy and homogeneity normally after those shits?
Yeah. Yeah, so this is this is the idea that at large scales you would get the isotropic behavior. So H would go to a constant, and then you get the isotropic behavior in all directions. No, this was a guess. The fact that it looks like this, just a function times the spatial metric, was a guess that at large distances it would be isotropic. But this is a full solution that is valid outside of all of the black holes.
زي ما بقول كويس شويه معاهم بس فوق معاهم 1 1